Okay, so you're staring down your computer vision midterm, totally panicked about units 3 and 4? Take a deep breath. You are in exactly the right place. Welcome to the explainer that is literally going to save your grade. I'm going to be your virtual TA today. We are doing a rapid-fire crash course covering absolutely everything you might have missed in lectures regarding OpenCV and digital image processing. Here's our game plan. We'll blast through OpenCV basics, hit filters and morphology, cover image enhancement, dive into alignment and registration, break down the OCR document processing pipeline, and wrap it all up with a rapid-fire exam revision.
All right, let's jump straight into Section 1, OpenCV Basics. So, OpenCV, the open source computer vision library. This is the absolute foundation for everything we're doing. It's the go-to open source toolkit for reading, displaying, and transforming images. But hey, listen up, because professors absolutely love to test this trivia point. When OpenCV reads a color image, it doesn't use the standard RGB format. Nope, it reads it in BGR order, blue, green, red. Definitely write that down.
You know, pretty much every exam question about a pipeline builds directly on this core workflow. It's 5 simple steps. You take your input image, you read it, you pre-process it, which kind of means resizing it or converting it to grayscale, then you process or analyze it, and finally, you display or save the result. If you get hit with a long answer question asking you to design a solution, always frame your answer using these exact 5 steps.
Moving right along to Section 2, filters, edges, and morphology.
Okay, matching the blur type to its exact exam keyword is an absolute must. Think of it like a matching game. If you see a multiple choice question asking how to just smooth an image, especially right before edge detection, your answer is Gaussian blur. Now, if the question brings up salt and pepper noise, you know, those annoying random white and black pixels, bam, immediately select median blur. And if they want you to smooth the image but preserve those crisp, sharp edges, that is for sure the bilateral filter. Memorize these pairings, guys.
Speaking of edge detection, let's look at the Canny edge detection workflow. Canny doesn't just magically find lines. It's actually a multi-stage logic puzzle. First up, we apply noise reduction, usually that Gaussian smoothing we literally just talked about. Then we calculate the gradients, apply non-maximum suppression to thin out the edges, use double thresholding to pick out the strong and weak edges, and finally, we track those edges to link them all together. Watch out for this classic trick question, though. Canny versus Sobel. Canny is used for finding exact boundaries. Basically, Canny equals edges. Sobel, on the flip side, detects horizontal and vertical intensity changes. So Sobel equals directional gradients. If the question specifically asks for directional gradients, do not pick Canny. It's a trap. All right, next up is morphological image processing. Don't let the big name scare you. Just think of these as shape changers. They modify the structure of objects in binary or just black and white images. And the way they do this is by sliding a tiny little matrix over the image, which in OpenCV is called a structuring element or a kernel. You really need to lock in these memory cues for the 2 foundational operations here. Erosion removes pixels from boundaries, just like real-world soil erosion. It shrinks things down. Dilation, on the other hand, adds pixels to boundaries. Think of your pupils dilating in the dark. It expands. So keep it simple. Erosion equals shrink, dilation equals expand. From those 2 basics, we get our compound operations. Opening is literally just erosion followed by dilation. Closing is the exact reverse, dilation followed by erosion. Here is your ultimate cheat code for the exam. Opening equals remove, as in it removes small noise and objects. Closing equals fill. It fills small holes and closes gaps. Oh, and for bonus points, remember that top hat highlights the bright details, while black hat highlights the dark details.
Let's pivot to Section 3, Image Enhancement Fundamentals.
So, we often use histograms, which just show the distribution of pixel intensities to fix contrast in an image. You've got to memorize this vital difference. Histogram equalization, that's global. It redistributes values across the entire image. But CLAH, which stands for Contrast-Limited Adaptive Histogram Equalization, is local. It enhances local regions, making it way better for images with uneven lighting, like a document half in shadow. And hey, that exact same local logic applies to adaptive thresholding, which calculates different thresholds for different little regions instead of just using one global value. Let's quickly look at the 2 opposite sides of the enhancement coin. Smoothing reduces noise and unwanted details. It kind of softens things up.
Sharpening does the exact reverse. It emphasizes edges and fine details, often using a technique known as unsharp masking. Just remember, smoothing equals reduced noise, sharpening equals enhanced details.
Moving on to Section 4, Alignment and Registration.
Okay, here's another massive exam distinction you need to highlight. An affine transformation can translate, rotate, scale, and shear, but its defining feature is that it preserves straight and parallel lines. Perspective transformation, however, actually changes the viewpoint of an image. So if the exam asks how to correct a document you snapped a photo of at a super weird angle, the answer is always perspective transformation. Affine equals parallel lines preserved. Perspective equals viewpoint correction. Now, when we want to combine multiple images, we use image registration. Basically, just define registration as alignment. You have a reference image, you have a moving image, and you want them to match up perfectly. There are 3 types you need to know. Rigid allows for translation and rotation, affine adds in scaling and shearing, and non-rigid actually allows the object to deform, kind of like tracking a beating heart in a medical scan. The feature-based registration pipeline breaks down really logically into these steps. First, input your 2 images. Next, use algorithms like SIFT or ORB for feature detection. That's finding the really distinctive points in both images. Then, you match those corresponding features, estimate the math, the transformation required to align them, and finally, warp the moving image into place.
So what is that mathematical transformation called when we're dealing with flat surfaces? It's a homography. You need to ensure you associate the word homography directly with a 3x3 projective transformation matrix. If you're building a panorama or aligning scanned documents, you are finding the homography matrix to stitch the whole shebang together. Almost there! Section 5, OCR Document Processing Pipeline. The whole concept of OCR, optical character recognition, is simply converting image text into machine-readable text. The pipeline starts with acquiring the image, then preprocessing it with grayscale and thresholding to really make the text pop. Next comes detecting the text regions, recognizing the actual characters, and finally generating the text output. Oh, and definitely note that in Python, the PyTesseract library is the standard go-to interface used to actually perform this OCR task. But what if you want to write text back onto an image? Let's clarify exactly when to use which library, because this trips people up. OpenCV is brilliant for computer vision and complex image processing, but honestly, its text drawing is super basic. Pillow, or Pile, is an imaging library built specifically for image manipulation, drawing, and using custom typography and fonts. So OpenCV equals computer vision. Pillow equals image manipulation and typography. All right, time for Section 6, Rapid Exam Revision. Get ready to screenshot. Let's rapid fire these essential functions. cv2.imread and imwrite are your bread and butter for reading and saving. cv2.cvcolor is how you convert your color space, like switching to grayscale. cv2.threshold separates regions based purely on pixel intensity. cv2.warp-affine applies that parallel line-preserving affine transformation, and cv2.find-homography calculates your 3x3 projective transformation matrix. Okay, you now have the structural blueprints, the exact vocabulary, and the distinct pipeline steps required to totally ace these units. I hope this explainer gave you exactly the focus you need. Let me leave you with this final thought. If a computer can be programmed to seamlessly interpret our complex visual world using just a few clever matrices and pipelines, what's stopping you from mastering this exam? You've got this. Good luck.